Systems of equations by substitution. Yesterday we introduced the concept of the system of equations, and we talked about how you can graph those systems of equations and find their shared solution by finding the point where they intersect. Well, today we're going to look at using another method for solving a system of equations, and that's called substitution. First thing we got to realize is that the word substitution in math is the equivalent to the word replacement in the English language. You can substitute something or replace it with something it is equivalent to. In order to replace it, they must have the same value. So a very elementary example of that would be our little system we have here. 8 plus 2 equals 10, and 6 plus 4 equals 10. Therefore, 8 plus 2 must equal 6 plus 4. What we're doing to get there is we're looking at this 10 here, and we're saying, I know that this 10 is also equal to this 6 plus 4. So therefore, because 10 is the same as 6 plus 4, I can rewrite this first equation, and I can get rid of the 10 and replace it with 6 plus 4, making 8 plus 2 equals 6 plus 4. Now, if anytime we're looking at multiple ways to solve problems, we have graphing, we have substitution as two different methods for solving systems. Anytime we're looking at that, we need to understand, when do I use substitution, when will I use graphing? And graphing is nice. It's a good visual way to look at where two lines intersect, the shared value. All that makes a lot of sense visually when graphing. However, oftentimes graphing is not realistic or efficient. The numbers might be too big, it might run off the board, or you simply just don't want to take the time to draw a graph. So it's not always going to be the realistic or efficient way to do things. So we'll also use substitution when we have one variable without a coefficient. So if anywhere in the problem you have just a lone x or a lone y, substitution is going to be the easiest method to use. So let's look at an example. Given this system of equations, x equals 2y minus 4, 3x minus 8y equals 12. You notice neither one is y equals, so therefore graphing is not very efficient. And also here we have x equals 2y minus 4. We have an x variable entirely by itself. There's no coefficient on the x, so that allows us to use substitution fairly easily. When we look at our substitution step, this is what it's going to look like. This is the part, the kind of big idea of the day that you must be able to understand. We know that x is equivalent to 2y minus 4. Because we know that, we can take this 2y minus 4 and plug it in for any x in the problem. So I look at my second equation and I see this x here. I'm going to replace that x with what x is equal to, which is 2y minus 4. So if you look at what we did here, we rewrote our equation. 3 times x, but instead of x, we put in 2y minus 4, and then we just completed the equation, minus 8y equals 12. One common mistake I see a lot is people want to leave an x in the problem. We are entirely substituting x. X is gone from our equation. We've replaced it entirely with 2y minus 4. What that allows us to do is that gives us an equation in one variable. You've done enough algebra to this point that you can solve accurately most any equation in one variable. So here we have 3 times 2y minus 4. We see parentheses, we think distribute. That gives us 6y minus 12 minus 8y equals 12. Combine your like terms, negative 2y minus 12 equals 12. Add 12 to both sides, and you get negative 2y equals 24. We divide by negative 2 and get y equals negative 12. Now, the next thing we have to do, we are not done with the problem. This is a mistake a lot of people make because they think, oh, I've got my variable, I'm done. This is a system of equations. We are working with two variables, so you must have two answers. So when we have y equals negative 12, we have to go back to the original problem and say, if I know y, can I find x? And I can by using substitution again. I go back to my original equation here and I say, I now know what y is. So therefore, I can replace y with negative 12. So I have x equals 2 times negative 12 minus 4, which gives us negative 28. So therefore we can think about that in two ways. We can write our answer as x equals negative 28, y equals negative 12, or we can write it as a point, negative 28, negative 12, because that is another way we can write the answer, because we're finding that point where they intersect. And you see why graphing's not realistic here. I don't want to graph the point negative 28 and negative 12. All right. Now that we see the concept here, let's look at two more examples rather quickly. Our second example involves a common error. You see our system of equations, 8x minus 3y equals negative 20 and y equals 3x plus 6. We're going to use substitution, and we have y by itself. So in my first equation, I'm going to replace y with 3x plus 6. I've simply copied the exact same equation, but in place of y, I've put 3x plus 6. Now I see a parenthesis, so I'm going to distribute. This is our common error. We need to make sure we're being careful with our signs. This 3 carries a negative sign with it. So when I go to distribute, I have to consider that a negative 3, which gives me 8x minus 9x minus 18. I combine my like terms. Negative x minus 18 equals negative 20. I add 18 to both sides, and I divide by negative 1 to get my x value of 2. Once I have x, I am not done. I need to find y. Y is equal to 3x plus 6. So therefore, I'm going to replace x with 2, and do 3 times 2 plus 6 to get 12. That gets us our answer of x is 2, y is 12. And again, we can always write our answer as a point if we wanted to. Our final example is one where you have to do one extra step, where you have to solve for a variable first. If you look at our system of equations here, you'll recognize 3 out of the 4 variables have coefficients, 1 does not. In the first equation, we have a y that does not have a coefficient. That makes it easy to solve for y. In order to use substitution, we have to have x equals or y equals. So we take our first equation and we rewrite it as y equals 23 minus 3x. Now, I have not changed the problem in any way. I've simply rewritten the first equation. So therefore, if it helps some of us, I'm going to cross off that first equation, because that way we're really working with a new system here. And now our new system is exactly like what we did previously. I can replace y in the first equation with 23 minus 3x. So I get 2x plus 3 times 23 minus 3x. Now once you're here, everything ends up being the same in every problem. I distribute, combine like terms, subtract, and divide, giving me x equals 9. Once I have my x, I need to find my y. I plug back into my original equation, and again, you notice I use my new equation here that I created because it's equal to my original equation, 3x plus y equals 23. I can use that just as well as the original. I plug 9 in, I get negative 4, so therefore if I would have solved those two equations for y and graphed them, they would have intersected at the point 9 comma negative 4. So there's my solution. Alright, so tomorrow we'll be solving systems in class, and then we'll get on to our third method in our video tomorrow.